In this lecture, we will look at machine failure and how to use stress in order to analyze or do static loading failure analysis. In studying failure analysis, we first look at kind of load, and the kind of load can either be static, which is the topic of this lecture, or variable load that can be repeated, fluctuating, shock, and random load, any changing load. So in this lecture, we will only talk about load that doesn't change, doesn't increase, doesn't decrease, doesn't change point of action. The second important thing is type of material. We have two types of material. We have brittle material, we have ductile material. So each type of material has failure theory that can be used to study failure. And the third thing is the manufacturing process. This can increase stresses if we have change in dimension, if we have holes or grooves or scratches in the face. This can increase stress in the location of calculation. Okay, so this is just failure examples. I'll skip that. So this is the stress concentration. When you calculate stress, let's consider this cross section here. In this cross section, stress is equal, doesn't change. I mean, you calculate stress at any location, it will be the same. Load by area. But in this cross section, because we have hole here, if failure will happen, it will start at these points. And that's because we have stress concentration in these points, which means stress is greatest at these locations. So stress will be more in these points. To increase the stress in our calculation, we add stress concentration factor. Okay? So stress concentration factor can be calculated or can be found based on the shape and type of stresses. You can use appendix A15 and A16 for common examples. This appendix is in your textbook, Shigley Mechanical Engineering Design. So I have two examples here, two different examples. One for normal stress in a plate with the hole. You need diameter of the hole and W, which is the width of the hole, to get this ratio. And let's say, for example, diameter by width was 0.3. So from 0.3 you go up and you can read stress concentration factor on the vertical axis. The same with the second figure, where we have a shaft with change in diameter, but this shaft is subject to bending moment. Okay, so you need two ratios. You need larger diameter by smaller diameter, and you need R by D. R is this one. R is that fillet radius. Okay, so we need static failure theories to study failure. In previous lecture, you learned how to calculate stress, and stress can be calculated in perpendicular axis. So let's say sigma x and sigma y and sigma z, with also shear stress. And then we went one step further and we calculated principal stresses, sigma 1 and sigma 2. So we have so many stresses, but the material only has one strength. The failure theories will relate or connect all these stresses to the strength of the material, and will help you to prevent stress and to select a material that can withstand all these stresses. Okay, so this first or the simple failure theory will say, okay, let's say I have principal stress sigma 1 of 150 megapascal and sigma 2 of 200 megapascal. So to be safe, I will choose a strength of larger than largest stress, which is 200 megapascal. So this axis I will draw sigma 1, and in the vertical axis I'll draw sigma 2, and this is the limit. So I will say whether in tension or compression, any point inside this envelope is a safe area. So if my stress is less than strength, that means we are safe. If my stress is outside the box, that means my stress is larger than strength, and then we expect failure. So this simple check is not valid, especially in this quadrant where we have positive stress and negative stress, or tension and compression. So we need more accurate theory.